Thank you so much to Britta and Kenny for having me here. I'm very excited to be here. Can everybody hear me and see my screen okay?
Yep, it's perfect.
Thank you. So I'm going to be talking about, well, my name is Kate LoMedico Marriott. I am currently a grad student studying earth science education at the American Museum of Natural History, but I'm also an adjunct professor at Brooklyn College. And I was recently inducted without my knowledge into the New York Academy of Sciences, which is really cool. So I'm just listing that now because it's amazing. Uh, so I'm going to be talking about two things. My recent or forthcoming book, Evolution of the Ammonoids, and a lesson that I created for my college students based on my book, which is really just like a hour-long lesson for college students called Mass Extinctions as Climate Disasters. So if you don't know, ammonoids are a type of cephalopod mollusk, so they're an octopus relative, and they were around from the early Devonian period to the early Paleogene. So they were around from about 409 million years ago to about 250,000 years after the dinosaurs went extinct. And they had an external shell. And so this tends to make people think that they're related closely to the chambered nautilus, but they're not. They're most closely related to things like octopuses and squid, for some anatomical reasons that I think we get into later in this PowerPoint. If you need a cultural reference, they are the inspiration for the Pokemon Ammonite, and they are massively diverse, and there are just so many of them. This was an extremely prolific group, extremely successful group of animals for millions of years. So again, ammonites superficially look like a chambered nautilus, but there's a lot of evolution that took place between nautiluses, which are essentially the ancestor of everything, and the things that we think of as ammonites. So we can think of octopuses and squid, which are the coauthors, and the ammonoids together as sister taxa, and nautiluses would essentially be our parent taxon. This is an image of a chambered nautilus that is supposed to be a GIF, but it's not functioning as one for some reason. So chambered nautilus means that our shell has chambers in it. So basically in both these shells in the image here, the outside wall has been sanded away. And what we see, these lines that we see on the shell, are going to be the edges of the chamber walls, the separations between these chambers. In a nautilus, which is the image on the left, we have straight walls. And in an ammonite, the image on the right, we have these really frilly patterns. They can get incredibly complex. They can be really simple, they can be really complex. There's a variety of shapes that these squiggly lines come in. Something that's really important here is that the nautilus with the straight shell, or the straight suture line, has a really thick suture line, and the ammonite has a very thin one. So there is a perfect converse variation here between complexity of the suture line and how thick it is. So the more complex these squiggles get, the thinner the suture line is going to be, the thinner the chamber wall will be as well. So because ammonites were so diverse and they were so populous, they are what we call index fossils. In paleontology, an index fossil is a type of fossil that geologists use to delineate periods of time. So the entire geologic timescale that everybody in geology uses was created using fossils. Things like the Jurassic period, the Devonian period, all those names that you may have heard, those were created largely using fossils. Index fossils have four main criteria. A fossil needs to be geographically widespread. So if I can find the fossil in England and I can find the same fossil in Eastern Russia, that's a good sign that it might be an index fossil. It needs to be abundant. So these things needed to breed like rabbits. They need to be everywhere. There need to be thousands of them. And if I'm going out into the field, into a place that could have that species, I need to have a high amount of certitude that I'm going to probably find a fossil related to that species. what makes ammonites really great index fossils is that they are easily identifiable from each other. They are so diverse. So we probably think of ammonites as like the Fibonacci spiral, but there were straight ones. There were all sorts of shapes. And they have all sorts of little ornamentations on their shells. So they're very easy to tell from each other. And then finally, we want to have a short-lived temporal range. So they want to live and die really fast. So they only take up a very thin layer in the rock record. So for example, just to picture how successful versus unsuccessful index fossils work in a stratigraphic section, if we look at fossil C in the image on the right, sorry, the first appearance datum for fossil C, so FAD just stands for first appearance datum, and that's going to be in bed 3. And then the last appearance datum, LAD, appears at the top of unit 6. But if we look at the ammonite in this picture, fossil D, the first appearance and the last appearance occur in just one rock unit. So the resolution of time, we can be a lot more descriptive with specifically that period of time, because that fossil was only there for a very fine point in the rock record. So because of all these things, because they're so diverse, they're all over the place, they live for short bursts of time, ammonites are amazing index fossils. Many of them lived for as little as 1,000,000 years. There are a couple of species that were only around for about 200,000 years. Because geologists are thinking in hundreds of millions of years most of the time, this is a really short period of time for us. The shells, again, are really, really diverse. We're going to see a lot of them. And there were almost 20,000 species of ammonoids in the entire run of their history on Earth. In total, between fossil and living species, nautiluses only have about 2,500 species. And in the entire history of Earth, there have only been about 5,400 extinct or living mammal species. So 10 to 20,000 species for a group of animals, that's on the order of insects. This is a massively successful group. Something that we have to talk about with ammonites, because they lived for such a long period of time, is something called a mass extinction. And you've probably heard this term before. Mass extinctions have a pretty specific definition, though. These are catastrophic events in the fossil record where we see the last appearance datum for a majority of all the species that existed at that time at the same time. There's something called a minor extinction. These are actually pretty large events. These will claim a huge amount of taxa as well. There's really nothing minor about them. But both these things, mass extinction and minor extinction, these are large, significant events where we lose an enormous amount of biodiversity. In a mass extinction, it's usually the majority. When this happens, when we see these disappearance of fossil species out of nowhere, suddenly sharply cut off, it's often accompanied by non-gradual changes in the rock layers and the sediment where you would find them. So these two images on the right, these are both of the KPG boundary. This is the end of the Cretaceous period. The image on the bottom is the father and son duo who first described it, and the image on the top is from Colorado. This is an image where we can see a sharp contrast between the Cretaceous and the Paleogene above. Oops, skipped a slide. So we obviously can't determine a mass extinction severity in terms of like how many individual animals died, because there's no way to know that. We can barely know how many of a given species exist now. So we definitely can't know how many individuals in a species existed 70 million years ago. So we determine this mostly in terms of the number of species, genera, or families lost, just overall biodiversity losses. Additionally, whenever we have fossil preservation is really rare. Even if you have a kind of common fossil preservation is pretty rare. So if you have one fossil specimen, it's representative of an unknown number of other individuals. Another topic that's going to come up here a lot is going to be something called ocean acidification. If you're teaching about environmental issues, you probably already talk about this on some level. So when greenhouse gases, CO2, methane, what have you, build up in the atmosphere, the ocean ends up absorbing them. And this causes the ocean to become warmer and more acidic. This can happen due to man-made causes, but it can also happen from a variety of natural causes as well. So basically, when CO2 enters the atmosphere, enters the seawater from the atmosphere, it gets dissolved and it becomes carbonic acid and bicarbonate. And then we end up with this situation with lone carbon atoms who steal carbonate from seashells. And this is why we have animals essentially slowly dissolving in the ocean. So animals who have shells, if this happens really fast, and if these animals have thin or small shells, they're not easily going to be able to adjust. Mollusks and corals usually do really badly when these things happen, and thinner shells always fare the worst. So this image here is of a pteropod. It's a microscopic planktonic snail, and these guys are already starting to see some visible damage from ocean acidification. Another thing that is going to affect our ammonoid friends in the story is salinity, which can spike as a result of warming oceans. So when we have more energetically charged water, because it's warmer, we have more space between the molecules, and we end up having a greater capacity for water to hold on to salt. And so when we have periods of warmth in the ocean, we tend to end up having saltier areas. So this image on the bottom right, this is from 2011. This is not the Cretaceous period, but we can see that the warmest areas near the equator are also the saltiest areas. So if you have a very sudden climate change event, if you have a global warming spike, all of a sudden, it's very likely that not only will you have an acidity spike in the ocean, but you'll likely also have a salinity spike as well. And this can really wreak havoc on wildlife. So I'm sure that this is obvious to a lot of people, but there have been 5 confirmed mass extinctions. There's the Ordovician Silurian 440 million years ago, the Devonian extinction, which occurred in 2 pulses about 365 million years ago, the Permian Triassic extinction event, which was 252 million years ago. This is the big one, sometimes referred as the Great Dying. Then there's the Triassic Jurassic and the Cretaceous Paleogene, the one that killed the dinosaurs. So of these extinction events, ammonoids were impacted 4 of the 5 times, were impacted out of 4 of the 5 times. So they were impacted during the Devonian, Permian, Triassic, and Cretaceous, but not the Ordovician because they weren't around yet. So the first extinction event to impact ammonoids was the Devonian mass extinction. Ammonoids had become really, really successful during the Devonian period. They started to have this really rapid lifespan, and they started to reproduce really, really quickly. There was a lot of biodiversity. They were doing great. And then the Devonian mass extinction starts. This is a 2-event extinction over several million years. The Devonian period was a very warm time in the Earth's history, so we were in a mild greenhouse state where we have a lot of seawater coming up on land, so we have a lot of warm, shallow seas. We end up having the largest coral reefs of all time, and marine biodiversity just is great. It's doing wonderful, and that's great. But then when you have a greenhouse state, inevitably you're gonna probably have those greenhouse chickens come home to roost. The greenhouse gases start accumulating. And so we start to have a couple of things happen. So we have thermal shocks where suddenly the water gets way too warm. Think about if you have fish, when you bring home new fish from the pet store, you gotta let them acclimate or they shock. The same thing is true for wild animals in the ocean. We also see some evidence that there may have been ocean acidification, and there would have been changes to the salinity that could have harmed the ammonoids as well. So ammonoids do really badly in the Devonian mass extinction, as you might expect. But we know that certain ammonoids did okay. Certain ones were just done. They were never coming back. They were extinct. But certain ammonoids did okay. So these 2 images here are of 2 reproductive strategies in living cephalopods. The top images are of chambered nautiluses, and the bottom images are of an octopus or a squid or something like that. I'm not sure. So the image of the chambered nautilus, we have huge newborns coming out of those egg sacs. We also have very few egg sacs. A chambered nautilus will lay about 12 eggs at a time, if that. Many octopuses and squid will lay hundreds, if not thousands, of eggs at a time, and these are very tiny little babies who are born. So we are dealing with a essentially we're dealing with a miniature adult versus a paralarva. And so we have a lot of investment of energy and resources from the parents when we have a large baby, and then we have less investment to the individual babies for these octopodes. So it's probably a similar thing here. So for the Devonian mass extinction, the ammonoids that did okay were the ones whose parents invested a lot in them individually, the ones who got a big egg sac, a big yolk, and they were pretty much ready to go from the minute that they were born. The ammonites that really, the ammonoids that suffered were the ones that were born among thousands of siblings and had less parental investment. So this is an image from the book that my co-author Don thought of, and I made it, but he thought of it, and it was a good idea, I think. So we have some extinction events, and we've got a climate curve here. So at the beginning of the two events that make up the Devonian mass extinction, we've got some really big spikes in Delta C13. And then we start to see the reefs doing really badly, just like the reefs are doing badly right now. We start to see these giant Devonian reefs disappear when the Kalwasser and the starts to happen. This is like the major climate event of the Devonian period. We see a lot of fish go extinct. We see a lot of trilobites go extinct. And then one of the most common Devonian ammonoids, the Gephyroceres, go extinct as well. Then we have a little bit of a pulsating thing throughout the Kalwasser horizons where we go back and forth with our carbon. So once the reefs, the coral reefs disappear, we start to see sponge reefs take their place. We see the placoderms, these are armored fish, they disappear. And then we see something really interesting happen with ammonoids. So this ammonoid here, this is a triangular ammonoid, and it has a bunch of other anatomical features that are just absolutely bonkers. It's just a really weird thing. And this was in the group called the Clymenids. The Clymenids do really well during this period of time for some reason. And not only do the Clymenids do really well, but the Tornoceratids, this is another really common ammonoid from the Devonian period, these guys do well too. And then the Hagenberg event, which cuts off the end of the Devonian, and then we're in the Carboniferous, is when the Clymenids vanish, and then a more basic, a more simple ammonoid, the Prionoceratids, do absolutely fine, and sharks do fine. So we've got some survivors. We've got sharks, and we've got some very basic looking ammonoids. I want to point out that this ammonoid here, this Prionoceratid, it's a very like basic ammonoid anatomically, and that is going to be something that you want to keep in mind throughout this presentation. When we get to an extinction, which types of ammonoids are surviving, which ones are not making it through. So if we're looking at the Devonian mass extinction for lessons about how extinction events occur, some major takeaways would be things like global warming is detrimental to mollusks due to ocean acidification and temperature shocks. Larger, thicker eggs and shells can be a good first line of defense against ocean acidification. And when faced with a mass extinction, primitive traits or more general traits are usually a surer means of survival than more specialized traits. So when we think about the nautilus-like reproductive strategy, that is an older reproductive strategy, and it has a lot more success when we're dealing with sudden changes in the environment than something that just evolved recently. So skipping over the Carboniferous and the Permian, we get to the Permian mass extinction. And this is considered the most severe mass extinction event in the Earth's history that we know of. 90% of all species get wiped out, including about 70% of land species and as many as 97% of marine species, though I know that that number, people don't agree on it. Some people say 95, I say 97. It looks like 97 to me. This is where we see the absolute end to the trilobites and to the eurypterids. That's just it. No more trilobites after this point. And ammonoids get wiped out too. Only 3 genera of ammonoids survive this event. And only one of those 3 genera is credited with having repopulated the ocean with ammonoids in less than 1,000,000 years. So a million years is nothing in evolutionary time. We originally believed that ammonoids bounced back from this event in as much as 30 million years, but now we know that their biodiversity was back up to its pre-extinction numbers within 1,000,000 years, maybe less. So again, this is a time period where we start to see primitive traits winning out against derived traits. So a lot of these ammonoids, again, were primitive in terms of their reproductive strategy. They had larger babies, fewer babies, and more of an energetic or nutrient-based investment in the babies by the parents. So you have less babies overall, but you have more resources being passed down to them. And this ensures that individual babies have greater likelihoods of survival. So our hatchlings are going to be really, really big at this point, and they're going to have really simple suture patterns. So we talked at the beginning of this presentation about suture patterns. It's going to come up a couple times throughout the presentation. The Permian mass extinction was caused by something called the Siberian Traps, which are a large igneous province in northern Russia, and they're roughly the size of the continental US. There was volcanism in this region for 300,000 years. There were igneous intrusions and extrusions. So you would think that just having a continent-sized area of volcanic activity would be the culprit for some of these releases of CO2, because we know volcanoes release CO2. It turns out that the volcanic activity, the igneous extrusions, were not really the problem here. The igneous intrusions, so the depositing of igneous rock underground, was actually much worse than the igneous rocks that formed above ground, because what they were intruding into was coal. They were intruding into pure carbon. So we have a United States-sized area of pure carbon that is just being burned into the atmosphere for 300,000 years. And this is what results in us having a crazy amount of CO2 in the atmosphere, and it creates the biggest mass extinction of all time. So this would have been accompanied by unimaginable global warming, ocean acidification, sea level rise, crazy amount of destruction happening environmentally at this point. This is just nothing like we can imagine today. And again, we have just a couple of ammonoids that squeak by. This shark that I know a lot of people love, Helicoprion, hangs on a little bit after the Permian. It's not really a main character in the story, but it does hang on a little bit after the Permian. But as we can see here, all of these ammonoids with the Helicoprion are pretty simple looking. They're not heteromorphs. They're not ornamented. They're pretty basic. So I'm skipping over the Jurassic here because it didn't really hit ammonoids that hard in terms of a mass extinction event. I'm now going to differentiate between ammonoid and ammonite. So ammonites are just one type of ammonoid. We're talking about a group of animals called Ammonoidea, and the ammonites are just the ones from the Jurassic and the Cretaceous, and a couple from the Triassic. So the Triassic-Jurassic extinction was caused mostly by losing a lot of oxygen. There's a lot of disagreement in the community about why this oxygen was lost, and this caused a lot of asphyxiation type conditions for marine life, including our friends the ammonoids. The Cretaceous period is very, very, very interesting in terms of extinction events and global warming and ammonites. So by the Cretaceous period, we have the ocean just full of ammonites, full of other mollusks. We're dealing with a really big greenhouse state. So Earth is in this major greenhouse state, but it got there slowly. So there's like all of this amazing biodiversity. And even though we think of mollusks as doing really bad when we're in a greenhouse state, at this period of time, mollusks are getting really, really big. They're getting massive. So we have these giant clams. In the image at the top, the clam has been stood up, but they would have laid flat on the ocean floor. It's called an inoceramid. And then we also have giant ammonites as well. So Parapazosia is the one that people tend to think of. These are as big, if not bigger, than a person. We also have rudist bivalve reefs at this time. These are the big, long clams. So the Cretaceous period is very, very long. And minor extinction, again, is a misnomer. These are still very, very, very significant faunal turnovers. North America's Western Interior Seaway is a really good place to look at minor extinctions with ammonoids. So again, we're dealing with a major greenhouse state right now. And so we have sea level up on land pretty much everywhere in North America. We're close to a shoreline. There are periods in the Cretaceous where most of North America was underwater. So the first minor extinction that I'm going to talk about from the Cretaceous is called OAE1, or Oceanic Anoxic Event 1. And this was not a warming event. This was actually a cooling event. So global cooling can be as destructive as global warming. So instead of warming and putting the sea up on land, we have the opposite. We have a global regression where sea level drops, and we end up having most of our seawater, more and more of it gets stored in the ice caps. Because the world is so cold at this time, we end up having anoxia. So because the atmosphere and the water end up getting really dense and not having a lot of energy, we reduce mixing, and we have anoxia in the ocean. The sudden drop in temperatures and the loss of oxygen causes a lot of marine organisms to go extinct. A lot of different ammonites and inoceramid clams go extinct as well. But in this case, for some reason, they are pretty much immediately replaced by new similar species. The second oceanic anoxic event is the most extreme of the Cretaceous minor extinctions, and this was a warming event. So we've just come off of a cooling event, and now we have this extreme, very sudden warming event brought on by supervolcanism in the Caribbean. So we have another large igneous province in the Caribbean region. This starts pumping massive amounts of CO2 into the atmosphere, and the ice caps just melt really, really fast. This is the point in time at which we see the Western Interior Seaway cover most of North America's total area. Surprisingly, mollusks did absolutely fine relatively in this sudden climate change. So we don't really see any normal patterns of extinction related to the climate change. What we think happened here was that the salinity change was way more severe for these ammonoids. So this event happens so fast that we end up having a salinity spike pretty much immediately. And so because we've just changed the salinity of the water, so imagine you have a fish tank and you just dump an entire bag of salt into it. Everything in that fish tank is going to die. And so even if you're warming up the fish tank in the background, we're not going to say that you warming up the fish tank was the culprit. We're going to say that the salt was the culprit. And that's exactly what happened here. The ocean is on a little bit of a delay when it comes to climate change. It takes a little bit longer than the atmosphere to heat up. And so salinity just absolutely got out of control and probably killed most of those ammonoids. And then we get to the end of the Cretaceous period. This is the best known extinction in Earth's history because it's the one that killed the dinosaurs. A lot of people think that this event killed the ammonites as well, but it didn't. They did not go extinct here. I repeat, ammonites did not go extinct at the KPG boundary. They hang on for more than 250,000 years later. Oops. So the Chicxulub asteroid strikes the Earth, if you don't know. This is in the Yucatan Peninsula in Mexico. We have large terrestrial animals essentially getting baked by this event within hours of the collision. And then any terrestrial animals that are able to survive are usually burrowing. They're usually kind of small. And mammals end up faring better than reptiles because they were small, they were easily concealed, they were able to get themselves out of these conditions, whereas the dinosaurs were too big to burrow or hide from it. Things are kind of similar in the ocean to the way that it works on land. Like I know that you've probably heard that story about why dinosaurs died and mammals didn't. Ammonites kind of did the same thing. So there's several genera of ammonites that are found around the world in sediment up to 300,000 years later than the collision, later than the iridium anomaly. Overwhelmingly, these tend to be seafloor dwelling or demersal ammonites who live near the seafloor, who have a pretty large amount of water between themselves and the surface. Seafloor ecosystems tend to be on a delay from shallow dwelling and terrestrial extinction events. So even if the extinction event is inevitably going to make its way down to the bottom of the ocean, it's going to happen quite a bit later than it did on land. So we can tell where ammonites live in the ocean based on their isotope shell geochemistry. So if they have a lot of delta C13, then they probably lived on the seafloor. If they have a lot of delta O18, they probably lived closer to the surface. This can also be used to tell you how warm or cold the water was in the climate where the ammonite or whatever mollusk lived. So about 5 genera survived again, and all of these genera were ones that had relatively unfixed positions in the water column. So of the ammonites that survived, a lot of them were what we call scaphitids. These are a type of heteromorphic, crazy-looking ammonite. They're actually this red thing here. This is a scaphitid. This is Hoploscaphites, and it's one of the latest known ammonites. It's going to be important in a minute. This one here is Discoscaphites. This is how scientists proved that ammonites in New Jersey survived the KPG boundary. So how do we know that scaphitids did okay after the KPG boundary? So in all of these shells, there are things called microfossils. We've got foraminifera, diatoms, all sorts of little microscopic plankton that would have been found in the inner chambers of this particular ammonite, which is a Hoploscaphites from Europe. I think it's from Denmark. And this particular ammonite's chambers contain foraminifera and diatoms from the Paleogene period, not from the Cretaceous period. These diatoms are from hundreds of thousands of years after the dinosaurs went extinct. So when you have a shell, when you have a hollow chambered shell, and you have sediment wash into it, that sediment becomes rock relatively fast. It's certainly not going to get flushed out of that shell after the shell has been buried. Especially given that our shell here has intact sutures. So if you were to flush a bunch of sediment in and then violently flush it out really fast, you would destroy all these squiggle patterns. But the squiggle patterns are intact. So we know that any of the microfossils inside this shell are from the time that this ammonite lived, which was hundreds of thousands of years after the death of the dinosaurs. But only 5 genera survived. In the Permian extinction, only 3 genera survived. So you'd kind of think that there would be maybe a little more hope for ammonites at the end of the Cretaceous period than there were at the end of the Permian, because we've got 2 whole genera that make it out. This is not true. So it's intuitive that we would have a similar bottleneck event where just a couple species make it and then they re-explode the biodiversity. But we're now in the Paleogene period. We're no longer in the Cretaceous period. And the Paleogene period is dominated by what we call hyperthermal events. So you may have heard of the PETM, the thermal maximum, which occurs much later than this. It's the most famous one, and it's the one that made scientists realize there's actually a pattern throughout the Paleogene of these things, these spikes in the climate called hyperthermal events, where we have an unimaginable amount of greenhouse gas. We've got warm, acidic, salty oceans. And the Paleogene hyperthermal events were absolutely extreme. So I know that a lot of people are working on this question because it's a big question in paleontology. So I've been working on this for about 2 years, and I know some other people who have been working on it for a bit longer. It's very hard to get a paper like this through review, if you don't know, because it's a controversial topic. It's a really hot topic. Nobody wants it to be wrong. There's a whole world about it. So this is a really, really challenging issue. But the first hyperthermal event was called the Dan-C2 event, and this occurred at least about 200,000 years after the KPG impact. So we have the Dan-C2, which was one of the most extreme climate events in the history of the Paleogene, the period right after the Cretaceous. And we have ammonites who are evolved to endure the Cretaceous, but they're not evolved to endure a sudden and very extreme shift in the climate, such as the Dan-C2 event. Additionally, ammonites' numbers are already very, very compromised by the KPG boundary. They haven't yet fully recovered. So a lot of ammonites did go extinct in the Cretaceous, but not all of them. There were still ammonites well into the Danian, to the Paleogene. So if this was normal times when it happened, if there were more species, and we weren't already decimated, maybe ammonites could have made it through one more time, but there's only 5. And this is a very, very extreme shock that occurs once things start to calm down. We have this immediate global warming catastrophe. And so ammonites have a little bit of a damned if you do, damned if you don't situation on their hands, because again, going back to sutures, if you have very, very complex sutures, you got a really thin shell. And if you have less complex sutures, you have a thicker shell. So you're a little bit safer from ocean acidification. But we know from pathological specimens of ammonites that the ones with really simple shells do not have anywhere near as much self-healing ability as the ones with complex shells. So either you can have really great self-healing ability, or you can be resistant to acidification in the first place, but you can't have both. So again, this is a little bit of a damned if you do, damned if you don't. We have either a really thick shell that's hard to corrode chemically, or we have a thin shell which is easy to corrode but easier to heal as well. So this is where I am in terms of my research on this. So there's a perfect relationship 100% of the time, where the more complicated these suture patterns get, the thinner that shell is going to be proportionally to the whole ammonite. And so when we have really, really, really complex shells like the one on the right, we end up having great self-healing ability. But if we have a simpler suture, we're going to have no real healing ability, but we might be able to resist acidification a lot better. So these are three of the ammonites that we see some examples of post-Cretaceous. We've got Haploscophites, Baculites, and Pachydiscus. Those are the three sutures that I included, and these are the ammonites that you would find those sutures on. So long after ammonites go extinct, nature actually tried and failed to remake them several times. But you can't remake a species that's gone extinct. Evolution is a one-way ticket, and even if it's really similar, a species is not going to be the same as another species that went extinct. The reason for these similarities is, of course, evolutionary pressures being the same. No matter how similar those evolutionary pressures can drive two species to be, they will never be the same species, and ultimately, they're going to have some kind of ancestral trait that reflects that. We call this convergent evolution. So in the late Oligocene, in the early Miocene, about 23.5 million years ago, we start to see nautiluses and octopuses both start to produce an answer to the ammonoids, which had gone extinct more than 40 million years prior. Neither one of these is going to be an ammonoid, but they're both going to be other types of cephalopods that have ammonoid-like traits. The reason I believe that nature and evolution were able to get away with this little ammonite experiment in the Oligocene, is because we have a really cool climate, we have alkaline oceans. This is a really safe period of time to have evolutionary shell experiments. So the first one is Eturia. This is a nautilus. But if you notice, this nautilus has a chevron little thing in its suture line. So this is a nautilus that has evolved a saddle, essentially, or a lobe, a complication in its suture line. It's deviated from the straight pattern that nautiluses normally have. And then we have argonauts, which are a type of octopus. These have a paper-thin shell in the females only. They are not attached to their shell. They just use it as an egg case. But these things are not ammonites. They're pretty close to being like an ammonite, but they're not ammonites. So Eturia is a nautilus with an ammonoid-like suture. Argonauta is an octopus with an ammonoid-like shell. Argonauts are really cool because, to me at least, they are basically the closest thing we have to a living ammonite. We only learned in the past couple of years exactly how they secrete their shell, which is not like ammonoids or nautiloids. They secrete their shell from a webbing between their two front arms. Again, the Argonaut first came about in the late Oligocene, early Miocene. So these are animals that evolved for a very alkaline and cool ocean, not what they're experiencing today. And actually, Argonauts are pretty rare in the fossil record. They're not an overly successful group. Their shells are extremely thin, and once that nice little alkaline period in the Miocene was over, they were not doing all that well. And as you can imagine, they are alive today. They're not doing that well today. This photo on the right is of an Argonaut whose shell has broken, and you can see that her eggs are starting to leak out. So this won't hurt her because she's not permanently attached to her shell, but her eggs are probably compromised now. So to me, cephalopods, ammonites, paleontology are really cool ways to talk about climate change and conservation. There's a whole field called conservation paleobiology. Normally it applies to living mollusks with shells, such as oysters, but I personally think cephalopods are a really cool thing to look at through an environmental lens. Paleontologists also kind of get dismissed a lot of the time as just like rock collectors, as dinosaur people, but we understand the mechanisms for stress responses in animals going all the way back millions of years. And we're able to predict how living animals might respond to similar crises, and whether or not certain animals have a chance of surviving without interference. So we know that redistribution, moving to a new habitat, is an age-old stress response in cephalopods, and we're starting to see that with octopuses from climate change. There may have been ammonite migrations in response to some of these extinction events that we talked about, where the climate shifted suddenly. That is my entire presentation.
All right, thank you so much, Kate. That was excellent. And thank you for everybody who
Thank you.
attended that live. My name is Kenny Coogan. I am the education coordinator for the Center for Inquiry. And you just attended a wonderful, wonderful TIES webinar. It's the first of our school year, our 2023-2024 school year. We have a lot of webinars coming up in September and October, which I'm excited for, and they're going to carry on all the way through May. And for some reason, we have this theme of aquatic evolution. So that's what you're going to hear for the next couple of weeks. This is the Teacher Institute for Evolutionary Science. It's one of the 3 branches of the education under Center for Inquiry. And we have a website, tieseducation.org. We are also on Twitter, we're on Facebook, and we're on YouTube. Our YouTube page is where you can go and see our playlists, and I've kind of orchestrated them so they're by theme and by topic. So if you're teaching middle school and high school biology, you can go to those specific playlists. And all of our webinars are posted there as well. Now, like I foreshadowed, we have a lot of really exciting webinars coming up. You can go to our Facebook page or our website to register for the webinars or to at least save the date. I do have one here posted on Facebook that isn't hosted by TIES. It's hosted by the International Union of Conservation of Nature. It's an Arthur group, but it's going to be about ground sloths and their evolution. And I think kids are really going to enjoy learning about ancient sea sloths as well. Now, we published a book. It's called On Teaching Evolution. It is a great reference, a resource for teachers. And the best part about it is we're having a BOGO deal. You buy one, you get one free. So that means you can give one to your favorite teacher friend. I mentioned that we have like 3 little sister education units. One of them is TIES, Teacher Institute for Evolutionary Science. But we also have Science Saves. And Science Saves is a program where we are promoting the idea that science is good and it's okay that science changes its opinion based on facts. So we are pro-science advocacy. For TIES, we're really all about science, biology. But for Science Saves, we are in all of the different curricula, and we are K through 12. All of our resources are free for all 3 of our programs. And then the last program I wanted to talk to you about was Generation Skeptics. We also have educational resources, ELA, science, math, everything. And we want to promote skeptical thinking. We want our students to be able to realize if they're being duped or not. Now, something that I really want to emphasize is if you want to have an expert in your classroom with one of these major topics, or even if you come up with another topic that you can think about skeptics, please give us email and we will connect you for free with an expert for them to zoom into your classroom. Let's start off with Katie asked, do you study more than ammonoids? And I asked that because Donald Prothero, who I believe you know,
Yes.
he said that he heard you talking about camels before we started recording. So if you wanted to maybe give us a little teaser about what you were talking about before this.
Yeah, so Don and I are working on camels and rhinos and a couple other mammals. So I am an Ammonite person, and Don has graciously allowed me to like glom onto his group of grad students and gain additional research experience. So yeah, we've been working on mostly systematics of camels and trying to describe a couple new ones.
And I'll also mention that Don is a supporter of the Center for Inquiry, and you can go to their
Yes.
YouTube page and see an excellent presentation from him. So Stan has a couple of questions. Ammonoids, ammonites have been around for a long time. What was their key to their success that allowed them to survive so many extinctions? You did mention primitive traits. Do you have anything else to add to that?
Primitive traits is one. Distance from the surface of the ocean is another. Not necessarily having a fixed role in the environment, being adaptable. I'd say is a third one.
So the follow-up to that from Stan was, do you know if they occupied the same ecological niche, or did they have different niches?
That's a really good question. Ammonites and ammonoids in general occupied many different niches. So a lot of them lived like near methane seeps on the seafloor where there's like little oases of oxygen. The ones behind me, these are called Diplomacerus maximum, and they lived in what's now Antarctica. These lived in this downward flotation position. We believe that they had a pretty slow metabolism, and it's possible that they lived for up to 200 years, their lifespan. So they would have just dangled in kind of a neutral position, not super close to the surface, not super close to the seafloor. There are additional ammonites, so acanthoserids, which are like the bumpy, regular shaped ones, but they're bumpy. These guys lived, do I have one up here? I have one. Nope, that's not one. Okay, I tried. See, where's my ammonite? Comes up a lot. But acanthoserids are really common. They're probably the one that you think of when you think of an ammonite. These ones, along with a really weird shaped one called Eubostrichoceras, both lived in a fixed. So if the shoreline moved, both Acanthoceras and Eubostrichoceras moved as well. Yeah.
All right. You have about literally a dozen comments saying, great job, fantastic presentation. I learned so much. Ed, I'll just read one. Ed says, that was fantastic, Kate. You've answered several questions I've had about these things. Can't wait for the book. So Kate, can you tell us, so for the people who are attending the webinar live, I put a link in for your book, but can you tell us the name of your book one more time and where people can find it?
Thank you so much. The book is called Evolution of the Ammonoids. It's being published by CRC Press, and you can buy it from CRC or you can buy it on Amazon, Barnes & Noble, all those websites and stores.
All right, Kate, if you have time, we got 3 more questions.
Absolutely.
Okay, so Katie would like to know, do the different shell shapes help? Do you know what the purpose of the different shell shapes were for their?
So it's probably something that we call niche partitioning. So animals will specialize into a role in their environment over evolutionary time. This is probably just an extreme version of that. So if you remember, we talked about how all the chambers are empty. So we have a bunch of little empty chambers. And these chambers are connected by a tube of tissue that can allow either water or air to move. This is how they swim, essentially. So they're either pushing water into the chamber and they're becoming more heavy, or they're pushing water out of the chamber and they're becoming lighter. So many ammonites, but none of the ones I need. When you have like a regular shaped ammonite, what ends up happening is they kind of move like a chambered nautilus. They just move backwards. The ammonite, but they just kind of move backwards. They probably bob up and down as they adjust themselves. If you have something that's shaped like a corkscrew, so if I use my slinky, for example, that I've been playing with this whole time, when they move, because they're pushing water or air in and out of the slinky, that tube is going to follow the slinky pattern. And so that whole animal is going to rotate. So if you're familiar with some of my artwork, I reconstruct an ammonite called Didymosauros a lot of the time, and these are corkscrew shaped ammonites. When you have an open coil like this, you're going to have a lot of drag on that shell. You're not swimming very fast, and all you can do is kind of slowly rotate up and down in the water column all day long, probably just grazing microscopic crustaceans.
Pam would like to know, do we have any soft tissues in ammonoid fossils regarding reproduction, or is the reproduction, are we guessing on how they reproduce based on other?
Cam, that is a wonderful question, and I will send you a DM later, my friend, because that is literally on my bookshelf right now.
All right, very good. And then maybe two more questions. When we find an ammonoid fossil, how do we determine how old it was when it died?
So there's a couple ways that we can do that. We can use sort of the first appearance and the last appearance data of different organisms and what we call the fossil assemblage. So we know the dates of rocks relative to each other. That's usually the way we do it because we've kind of mapped out the Jurassic period and the Cretaceous period. We kind of know the relative age of rocks to each other through geologic correlation.
I think he's asking, like, how do we know if an animal's like 50 years or 200?
Oh, thank you. Thank you for the clarification. So ammonite shells are very similar to like a tree ring or to like a clamshell or a fish scale. Many different things in nature will produce an annual layer. And so we can see in ammonites, we have like a cold water layer and a warm water layer based on those isotopes, delta C13, delta O18. And so we can kind of see, okay, there's a warm cold pair, that's a year. And so, yeah, same concept as tree rings essentially, but with isotopes.
Very good. All right, and the last question is, we hope that teachers play this webinar for their middle school and high school students, or at least, segments of it, for students who want to discover a species, name a species, learn about fossils. Post high school, what advice do you have for them to get into the field?
My advice would be to just get into it. Honestly, like unfortunately, there's a lot of gatekeeping and you have to tune it out. There's also like practical challenges, like you can't get to a museum or you can't go out into the field easily because you live somewhere where there's just not a lot of fossils, and that prevents a lot of students. I've heard of a lot of students being prevented from pursuing it due to like disabilities and whatever. You actually don't need to go out in the field and be like a Jurassic Park person to do this. Something I learned from Dawn actually is that all of the greatest projects in paleontology are most likely collecting dust in a museum cabinet right now. They're not in the ground anymore. Additionally, there's a lot of open data online. There's the Open Dinosaur Project, if dinosaurs are your thing. I don't know why anybody would get into dinosaurs though, like why when you have ammonites. I created a website called Ammodata, which if you don't mind, I'll just share my screen so you can see what this is about. So this is Ammodata, it's just a WordPress. But if you are a student and you want to study ammonites, you can just come to my website, ammodata.wordpress.com, and you can see that we have like thousands of data points for like everything to do with ammonites, their size, their shapes. I'm working on an isotope spreadsheet. There's a spreadsheet of the fractal dimensions of their suture patterns. That's how we measure their complexity. So the data's out there if you can't make it work any other way. But you should definitely just do it because nobody owns paleontology.
All right, well, with that comment, we're going to end our first webinar. It was fantastic, Kate. And once again, thank everyone who attended this live, and we hope that you attend our other webinars as well. So thank you once again, Kate.
Thank you all so much for having me and for coming, listening to me talk. Have a good night.